This is the 2012 Electricity and Electromagnetism Level 1 paper. Question 1, electrostatic dusters. A cleaner uses an electrostatic duster to clean an office. The duster is designed to pick up dust particles easily from surfaces, has fine nylon fibres attached to a stem, which is made of a non-conducting material as shown in the diagram below, which you can't see, but roughly there's further pictures down below. It's got a stem and it's got fine particles that stick off on the end to catch dust. A, while dust can table, the fibres on the duster become positively charged. Describe what causes the fibres to become charged. There's a picture below which is a bit better there. So what causes the fibres to become charged? First point you have to talk about is electrons being removed. So you're taking a negative charge away, leaving a positive charge. The electrons are removed because of the rubbing, or you can say friction, removes them. And more detail than you probably need to deal with here is that it is because the surfaces, the table and so forth, that the fibres are being rubbed against will attract the electrons stronger than the fibres will be able to hold on to them, so it becomes positively charged. Moving on, B. When the cleaner lifts the dust off the table surfaces, the nylon fibres point away from each other. As shown in the diagram on the right, explain why the nylon fibres point away from each other. It's because there's a couple of points you need to make, that they are all the same charge, or same positive charge. If they're all the same positive charge, with all these positive charges here, you need to state the effect that they will try to be as far away, will try to move as far as they can, so that to get a maximum even spread away from each other. And then the third point would be that this results in this even spread. Okay, C. When the charged duster is brought close to a dusty surface, the dust particles jump up and stick to the nylon fibres on the duster. The diagram below shows a dust particle attached to a fibre. Explain why the dust particle jumps up toward the nylon fibres and sticks to it. You can draw the charge distribution on the previous diagram to illustrate your answer. So we'll just put the pluses on our fibre there. Remember, the dust particle is neutral overall, has an equal number of protons and electrons to start with. So what's going to happen is as the positive duster comes near it, the electrons on the surface of the dust particle will move to the top. Okay, because the electrons can move, but the protons can't. The protons will stay in place, and you'll have this overall same charge that was on there previously, overall neutral, but with the negative on the top and the positive on the bottom, the dust particles are then attracted to the duster and then they'll touch it. So that's the first part, why it jumps up towards it, and why it sticks to it is, those electrons will go up and touch there. As it sticks to it, you'll maintain this charge separation, which keeps the positive, the negative, then the positive. It's a little bit like sticking magnets together, north to south, north to south, north to south. So you might have your north, south, north, south. But that's a property of the insulator, where it maintains that localized charge imbalance. Okay, so I think we've explained that pretty well and we've drawn the diagrams. D, the cleaner is wearing synthetic clothing. As he moves around, his body becomes positively charged. When he's just about to touch a metal doorknob, he sees a spark between his finger and the door handle. Describe what a spark is. It's movement of electrons, a very sudden movement of electrons. And you see the spark because this is going again beyond what you would have to know here, but you see the spark because it's effectively a higher temperature and you're causing the air to become plasma as the electrons are ripped off and it'll glow, something like that anyway, but that's more than what you need to know for this. Explain how his body becomes electrically neutral when he touches the doorknob. We'll go back up here and we've seen that he becomes positively charged. So the person is positively charged, touches the metal doorknob, which is neutral, and we're going to get a flow of electrons from the metal doorknob onto the person, and he'll become electrically neutral. What this is to do with is earthing, and we're assuming there is a large number of electrons available on that doorknob, so that when electrons jump off onto the person to make them electrically neutral, it also maintains electrical neutrality on the doorknob. Okay. And for the amount of electrons we're dealing with, there's probably way more available electrons on the conductor, the metal, than there are on the person. So you wouldn't notice the charge difference, because also the conductor will evenly spread throughout the whole, the amount of electrons that it has. So whereas the charge on an insulator becomes focused on a point on the surface, and then it feels quite strong, the effects are quite strong. Anyway, more detail than you need. Electrons move from the doorknob to the person. Part 3, the voltage between his body and the metal doorknob is 9,000 volts. When the cleaner is just about to touch the metal doorknob, an average current of that flows 2.5 times 10 to the minus 7. That's a very small current. High voltage, small current. Between his finger and the doorknob for a time of 0.0015 seconds. Calculated energy transferred by the spark. So energy is the power times the time. If you go back to the original formula, it's power is the rate of energy conversion, so it's energy over time, but we want it in this form. Energy is power times time. We have the time. We don't know the power yet, but we do know that the power is the current times the voltage. So we can do the current times the voltage, which is the P, times the T, and that'll give us the energy transferred by the spark. So just writing out what you'd have, 2.5 times by 10 to the minus 7 amps, and it's a good idea to put brackets around it. When you're calculating it, your calculator sometimes doesn't notice when you're doing exponents, so it's good to put the brackets. Times by the 9,000 volts, times by 0.0015 seconds. And I don't know what the answer is, but you put that in your calculator, and that's what you will get. Is that the end? That's the end.